All right, so let's look at optimality condition for convex optimization. So, you know from simple calculus that when you have a convex function, f is convex, and you want to minimize f of x, then you simply need to calculate the gradient of f and put it to 0. So x hat is an optimal point. So it is an optimal solution if this one holds. And let's look at the definition of convex function. So f is convex if f of y is greater or equal to f of x hat, which is your optimal solution, plus the inner product of gradient of f of x hat and y minus x. So if gradient of f is 0, then f of y is greater than equal to f of x hat, and this is just a definition for minimization of f of x. So x hat is an optimal solution. And so another example is sum of squares. Sum of squares. So the goal is to minimize the sum of I minus x, and you take the derivative, and then you find that it's so easy that AI minus x is equal to 0, and then you solve for this, and then you get x is equal to sum of those AIs, and because this one is n of x and this one is sigma AI, so x hat is 1 by n sum of sigma I. So mean of AI is important, especially if your objective function is a differentiable. I will show you that if this one is not differentiable and is some special form, then this would not be mean, it would be median. And so the ordinary least square could be another interesting example. You have some samples in machine learning. For example, your features are d-dimensional, and the ordinary least square, you want to minimize the sum of yi minus xi transpose beta 2. And so if you write it in the matrix notation, you will notice that this is very easy to calculate, that this is beta transpose x beta, and then the cross terms are just 2 beta transpose xy plus y transpose y. And if you just take the derivative with respect to beta, you will notice that this is 2 by n x transpose x beta minus 2x transpose y plus 0 is equal to 0, and you get the famous result for ordinary OLS, ordinary least square, which is x transpose x minus 1 x transpose y. So another example is a non-differentiable. So what do you do if you have a non-differentiable objective function? Non-differentiable. For example, so we say x hat is optimal if so we don't have differential, so we created the concept of subdifferential instead of differential, and I will explain it in a bit. And so for example, if you have a function which is non-smooth at some points, for example here it could have any derivative. You see, all of them are just tangent to that, so that's why any of G could be a solution of your subdifferential. So this is subdifferential. This is the generalization of differential when your function, where your objective is not smooth. So let's look at the definition of convex function. So f is convex function if f of y is greater than or equal to f of x plus the inner product of g and y minus x, as I said, for any y. And now g is one of the subdifferentials. So if 0 is in the subdifferential, so we can say that f of y is greater than equal to f of x plus 0. So if this holds for any y, that is the definition of saying that x hat is optimal solution. So you see how convex function plays an important role. So I want to show you another example, but this time it is non-smooth. So it is the sum of absolute values. So we have a1 to an, and the objective function you want to minimize is 1 by n, sum of absolute values of ai minus x. And I said that you just need to say that 0 is inside those, that inside the subdifferential. So the subdifferential of this non-smooth function is so simple because it's a sum of say some variables such as z, and z, because z is like this one, it's everywhere differentiable except 0, and in 0 I said you have many different subgradients. So that's why you can write that the subdifferential of z is equal to -1 if z is less than 0, if z is greater than 0 it's +1, and if z is equal to 0 at the points that we have non-smooth and non-differentiable point, so it's just anything between, so it's omega is in an interval between -1 and 1. And you see, if you work on this, you will notice that x is n by 2 and n by 2 plus 1. Of course, if first you make an order and then, so this is the median. So this objective function, your solution is a median. And the final and the last example I want to show you is the Lasso problem. And you have some points again in your machine learning or statistics. So xi is again your feature vector of size d. You have n observations. I is 1 to n. You have n observation and the feature size is d. And you want to minimize 1 plus n x beta minus y, L2 norm plus lambda and L1 norm. And L1 norm is just sum of absolute values. So if beta is optimal, so it is optimal if 0 is inside subdifferential of this function. And so we just calculate that and say 0 should be inside. The first term is just differentiable, so no problem, same as usual. Write it x transpose x beta minus y. And the second term, we have talked about it, we had an example, so you know it's just lambda subdifferential of beta. Subdifferential of beta, of norm of beta, this is a function. And so I said that beta is optimal if there exists a z such that zi is it's a sine function. If beta I is not 0, no problem at here, but the non-smoothness is when beta is equal to 0 for any I. It is inside this interval, so any number inside this interval. So finally, you can say that 0 is equal to 2 by n x transpose x beta minus y plus lambda z. And this is just an important approach to solving Lasso, but it is not complete. In the next lecture, I will talk about when you have a constraint set as well. So you want to minimize a function, but this time you will have a constraint, and your constraint is a convex set because it has some good properties. And that's it.